In this lecture, we're going to take a look at how to assess complexity. It's a very interesting topic, and what we'd like you to be able to do after completing this lesson is to appreciate the time and space complexity considerations for a function or program. Specifically, we're going to take a look at how to assess the time and space complexity of an algorithm and to understand the growth of space and time for an algorithm as a function of its input size. And we're also going to show you how to measure actual performance of a function in R using system.time. So what exactly is complexity? Well, complexity is a way to measure time and space required for an algorithm or a program to execute. So imagine that you build a function in R that carries out some kind of analysis algorithm or some kind of analysis procedure. So you would like to know how that algorithm's performance in terms of its runtime, its execution time, and its memory use is going to grow as the input size grows. So algorithmic complexity is concerned about how fast or slow a particular algorithm performs. Now we use that to compare algorithms and programs on a conceptual level. In other words, we're not going to really think about how many milliseconds something takes to run, although that's important too, but rather we're going to think about what would happen if you double the input or triple the input, or perhaps an input that's 100 times larger. How would the overall behavior of the program and its runtime and space time increase as well? Now, complexity is generally expressed as a numerical function. So the time required to run depends, of course, on various real factors. Processor speed, instruction set of the computer, disk speed, brand of compiler, programming language, data structure in use, and so on. So consequently, we're really not going to look and say, oh, that particular function takes 352.8 milliseconds to run. But rather what we're going to do is we estimate the time asymptotically. In other words, the value it will reach eventually as input size grows to infinity. And we do that by measuring what we call elementary steps. So let's take a look at an example to think about how that might apply to program analysis. So let's say you want to add two binary integers together, digit by digit, or in the case of binary integer, bit by bit. So adding a single bit is, of course, a single step in the computation. So if you have two n-bit integers, it would take n steps, one step for each of the n integers. So consequently, the total computational time for this would be some number of time per step multiplied by the number of steps. So the time of that program running is a function of its input size, in this case the number of bits in the integers. Now, of course, the actual execution time is very difficult to estimate because it depends on a lot of different factors. So, for example, if you've got an integer, an Intel i7 versus an i5, you run a different processor speed, you have a different operating system, Linux versus Mac OS versus Windows, programming language, maybe C code runs faster than Java code, which runs faster than R code, which runs different from JavaScript or Python. Heck, there could even be other processes running concurrently, like a database or networking downloads, or some kind of a socket interface. So programmers tend to compare and classify algorithms not based on how many milliseconds they take to run, but rather through the asymptotic growth as a function of the size of the input. Now, of course, you could conduct an experiment too. I mean, another way to compare different algorithms is to build them, write different versions of a program, and then simply run it and, measure how many milliseconds it takes. In fact, there is a function in R called system.time to which you pass a function as a parameter, and it will return you how many milliseconds that particular function took to execute. And once you've done numerous measurements for different input sizes, you could fit some kind of regression curve through this. So here's an example. You build some kind of an algorithm that runs and then try it out for 1 million, 2 million, 5 million, 10 million, 20 million different input elements in your algorithm, and then you observe with system.time the amount of time it takes to run. So with a million records, it might take 100 milliseconds to run. With 7 million records, it might take 600 milliseconds to run. 20 million takes close to 1600 milliseconds to run. And then what you can do is you can fit a regression line through this. Let's do right here. So if you take a look at this right here, you've got actual measurements here. So this would be the amount of time it actually took for 6 milliseconds. That's the amount of time it took for 13 milliseconds. And then you have different data points right along here for different input size measurements with system.time. And then all you do is you fit a regression line through all of this. And that's your regression equation. So you know that the amount of time it takes to run is 73.203 times the size of the input. So you know there is a linear relationship between the amount of time it takes to run and the input size. And if you look at the regression coefficient, it's a pretty strong regression model, has very good R squared, which is the coefficient of determination. So we know they have pretty good predictability in the variability of the data. But right now that's not really the point. The point here is that you've got an algorithm that is linearly related to the input size. So if you double the input size, it's going to take double the amount of time. If you quadruple the input size, it's going to take 4 times as long to go through this program. Of course, there's also often a significant difference between the best case, the worst case, and the average runtime of a program. For example, what if you need to sort a data set by year? Well, if it's already sorted, it'll be a lot faster to do that than if it weren't sorted. So generally we look for average case behavior and worst case behavior. We want to know in the worst case what's going to happen to this, and on average what's going to happen. So let's look at an example here. Suppose you need to search a column in a data frame or a vector for a specific element. In other words, find the data for the flight JB721 on 01/02/14. If that's the encoding we have for some kind of database of flights. We want to search for delays or search for number of passengers or whatever analysis we want to do. So the question becomes, how many string comparisons would you need to perform if there were n records or n flights in that data set? Well, on average, you would expect that you need to search about halfway through the vector or the data frame until you find that flight you're looking for. So it's n/2. In the worst case, it's going to be the very last one. And in the best case, it's going to be the first one. So in the worst case, you've got to search every single string, every single flight, so there would be n comparisons you would have to make. And in the best case, you would have to make one comparison. So there is a pretty big difference between average, worst, and best case in terms of runtime. But if you think asymptotically, just from a growth perspective, if you had a data frame with, let's say, 1,000 flights, it would take some amount of time to run. If you then had a data frame of 2,000 flights instead of 1,000, in other words, you have double the number of flights, how many comparisons would you think you need to make in the best case or in the worst case? Well, twice as many. Doesn't matter what n is. In the average case, you have to do n/2 comparisons, but it's still twice as many comparisons on average than if you had half the data set. So the actual runtime would need to be measured on a specific platform, but we can characterize the runtime behavior to increase linearly with the input size. So computer scientists use what's called big O notation to capture the essence of the worst case behavior of an algorithm or program. It's basically a function that describes the growth behavior of runtime or memory storage requirements for a program. So in the previous example, the program would have a time complexity of what's called O of n, meaning that in the worst case, so sort of its asymptotic behavior is O of n. It's related to the size of the input. So if you started with 1,000 records in a data set, it takes some amount of time to run. If you have 2,000, it'll take twice as long to run. If you have 10,000, it'll take 10 times as long to run. So this is what when we say that time increases linearly with the size of input. Now there's some other complexities too that are very common. O of 1 is a complexity that says it doesn't matter how big your input is, it always takes the same amount of time to run. It doesn't mean that it's going to take 1 second to run or 1 minute to run. It simply says O of 1. It's some amount of time, some constant amount of time. If time increases quadratically with the size of the input, it's O of n squared. If it's exponentially related, it's O of 2 to the power of n. The actual base doesn't really matter. Of course it matters for true performance, but we're trying to characterize behavior. If time increases logarithmic with the size of the input, meaning a very slow increase, it's log of n. If time increases log linearly, it's O of n log n. In fact, there are some common algorithms that take a certain amount of time to run, and it's important every time you call a library function that you know what its time and space complexity is. Often the program will tell you, but it's not always guaranteed they're going to tell you. Look at this picture right here. This tells you quite a bit about how program performance might increase as you increase the size of the input. Exponential increases dramatically faster than, for example, some kind of quadratic or polynomial time, which again is different than if you had linear time. Whoops, that's probably not the right thing to use here. Or this goes with the square root of n. This is a logarithmic. Logarithmic, notice it grows much, much slower as the size of the input increases. So if you go from, let's say, 20 to 25 times the amount of input, it increases very minor. This, of course, increases by the same amount. Quadratic, or the other polynomial, a cube, much faster. And exponential, of course, far, far faster. So it behooves you to know what time and space complexities of an algorithm either you write or that somebody writes for you. So we're going to take a look in the next part of this at how to assess and how to calculate the complexity of an algorithm.